Okay, welcome to week 3, part 2. So in week 1, we looked at the breadth-first search algorithm, which starts from a particular node in a graph and steps out 1 step away from that node, then 2 steps away from that node, then 3 steps away from that node. You can think of that as being sort of like searching a sequence of concentric circles moving out from the source node in order to find the shortest path to some target. This week we're going to take a look at depth-first search, which takes the opposite approach of breadth-first search. Whereas breadth-first search exhaustively visits all of the one-step neighbors first, and then exhaustively visits all of the two-step neighbors, and so forth, depth-first search starts with a one-step neighbor, then immediately jumps from there to a two-step neighbor, and from there to a three-step neighbor, and so on, until we hit a node that has no unvisited neighbors, and then we backtrack up the path that we have made, up the tree that we have made, until we find a node that does still have unvisited neighbors, and we plunge downward again from there. So visually, you can think of breadth-first search as sort of like the concentric rings that you get when you toss a rock into a pond, whereas depth-first search is more like a jagged lightning bolt with several branches that come down and abruptly stop. All right, so here on slide 2 is the graph of friends that we used in the previous lecture. Depth-first search is similar to the in-order traversal that we did with the binary search tree. That is, when we displayed the values in a binary search tree in order, our algorithm was first display values that are to the left of the current node, then display the value that's in the current node, then display the values that are to the right of the current node. This kind of naturally recursive definition is how we will implement our depth-first search. So, for example, looking at our graph, again, let's imagine that I'm starting from me in order to make sure that I am systematically visiting all of my neighbors. I'm going to start from me and visit the neighbor that's earliest in the alphabet first. So I'll go from me to A. Now in depth-first search, having reached A, I immediately go to A's next neighbor in alphabetical order, so that's B. All right, so I've gone from me to A to B. Now when I hit B, B has no unvisited neighbors, so I have to backtrack to see whether A has unvisited neighbors. Indeed, A does have an unvisited neighbor, so the next node I go to from A is J. J has a ton of unvisited neighbors. We'll handle these in alphabetical order. From J, we'll go to E. From E, we'll go to F. From F, we'll go to M. From M, we have a choice between S and T. We'll go to S. Then from S, we'll go to G. From G, we will go to Ed. From Ed, we have a choice between R and Z. We'll go to R. And once again, we hit a point where we have to backtrack because R has no unvisited neighbors. So we come back to Ed. We visit Z. Now, S has already been visited, so from Z, we're going to go to Y, and then to Q, and then to I. Well, I, at this point, has no unvisited neighbors, so we backtrack to Q. We visit X. X does not have any unvisited neighbors, so we have to backtrack quite a bit now. We backtrack to Q, and then to Y, to Z, to Ed, to G, and G has an unvisited neighbor, so we go to K from G. Eventually, this breadth-first search algorithm will visit every node in the connected component that includes me, but it's doing downward depth-first searches rather than outward breadth-first searches in order to accomplish this. Now, it is possible to define the depth-first search algorithm iteratively. Basically, it's very similar to the outline of the breadth-first search code, except that you use a stack to contain unvisited nodes rather than a queue. In fact, as a general thing, if you have a recursive algorithm, and want to turn that into an iterative algorithm, you frequently end up using a stack to support that. In effect, what you're doing is you're trading having a stack in your own code versus using the system's stack of symbol tables from function calls. Depth-first search, just like breadth-first search, is useful for identifying connected components. Either algorithm works fine for that. Depth-first search is better if you're trying to find something like a solution to a maze. If you're trying to get through a maze, you don't necessarily care about finding the shortest possible path through the maze. You just want to find a path as efficiently as possible. And it turns out, on average, that depth-first search will find a solution to the maze by visiting fewer total nodes than the relentless outward behavior of the depth-first search algorithm. Basically, any algorithm that requires backtracking, that is, you attempt to find a solution, you discover you can't go any further, so you back up and try another path, is where depth-first search comes in. Now, on the other hand, depth-first search is not at all useful for shortest path analysis. Depth-first search will find a path if a path exists, but offers no guarantee about whether that is the shortest path or not. Okay, so let's take a look at some almost working code for depth-first search. This is not quite working, but it's close. We have S, our set of nodes that we have visited. Of course, that starts as an empty set. We also have T, which is the tree of nodes that we have visited, starting from some root that we select. Here again, the tree is initially empty. And here's our depth-first search algorithm. The arguments are the representation of the graph, as we've had in the previous lecture. That is, the graph is a dictionary mapping each node to its directly connected nodes in alphabetical order. We specify the current node that we want to do our search from, and the parent from which we arrived at that current node. Now, let me skip ahead a slide. And we'll see that to kick this off, we specify our dictionary. We specify me as the current node. And me has no parent, so none is going to be the value of our parent when we're constructing this depth-first search tree starting from me. Okay, now, if the current node has not already been visited, then we're going to add the current node to the set that have been visited, and we're going to add the current node to the tree with its parent as the parent. Then, for each node in the immediate neighbors of the current node, and we've been careful to build our graph in such a way that these are alphabetical, at some level that doesn't really matter. It really just has to be an exhaustive list of all of the immediate neighbors. So for each neighbor of the current node, we're going to call DFS again with the neighbor as the current node and our own current node as the parent of that neighbor. And this recursion will go down through the tree until we eventually hit a node that is already in our set of visited nodes, at which point we will backtrack up the recursion. All right, so here on slide 5 is what we get when we call this algorithm for the first time. The tree just contains me. The parent of me is none. I should perhaps have written none here as the parent of me. And the set of nodes that I visited so far is just me. Now, recall from me that we're going to visit me's immediate neighbors alphabetically, so we're going to visit A first. And in the recursive call, we're going to visit A's immediate neighbors alphabetically, so we'll visit B next. When we hit B, B has no unvisited neighbors, so we have to backtrack. Here's what that first downward branch looks like. From me, we visit A. We add A to the tree with me as the parent, and we add A to the set. From A, we visit B. We add B to the tree with A as the parent, and also add B to the set. And now we have to backtrack, so we come back up to A. From A, the next alphabetical unvisited neighbor from A is J. And so we visited J, and that led to a quite long branch in our tree. From J, we went to E, then to F, then to M, then to S, then to G, then to Ed, and then to R. And when we got to R, we had to backtrack again. So we have this long downward branch in our depth first search before we have to backtrack. We backtrack up to Ed, and then we visited Z. And this backtracking continues, so we end up with our entire tree looking like this. When we backtrack to Ed, we find Z as an unvisited neighbor. From there, we visit Y, Q, I, backtrack to Q and visit X. Then we have to backtrack all the way up to G and visit K. Backtrack up to M and visit T. Backtrack to J and visit L and W. And finally, we end up backtracking all the way up to me and visit N and V. So what we can observe here is that depth-first search trees tend to be fairly tall and skinny with a small number of long branches. Breadth-first search, on the other hand, because we have to go out one step at a time in exhaustive fashion, breadth-first search trees tend to be fairly short and thick. Our depth-first search starting from me has found one connected component. If we want to find all the connected components using depth-first search, then we can simply traverse through the nodes in our graph. We'll discover that A is already in the set that we visited, B is already in the set that we visited, C is not in the set that we visited, shown here on slide 8. And so we build a new depth-first search tree starting from C as the root. Once we've done that, we'll discover that we have visited all 28 nodes that exist in our graph, and so we're done. And we have found 2 connected components in our graph. And here in slide 10 is the same diagram that we saw of the connected components that we found using breadth-first search last week. So, given a graph, when might you use breadth-first search? When might you use depth-first search? Well, breadth-first search is good if you need to find the shortest path that exists between some source and some target. That is, if you have your house at some location and your job at some other location, and you need to find the shortest path, whether that's by miles or by time, between your house and your job, that's not going to change very often, so it's probably worth spending the effort to figure out what the shortest possible path is. In fact, if you use an application like Google Maps to find the shortest distance between 2 points, this is how that's done. For example, here I've redisplayed slide 24 from last week's first part lecture. This was our shortest path tree from me to Ed, and gave me a path in which there were 6 nodes, me, I, Q, Y, Z, Ed, connecting me to Ed. On the other hand, we had to build a 20-node tree in order to find that shortest path. Now, using depth-first search, on the other hand, here I've displayed slide 7 from the current notes. It turns out that we only had to construct a 10-node tree in order to find a 9-node path from me to Ed. So the entire tree that we needed to construct was only half as large, although the path is a little bit longer. Okay, so our path is me, A, J, E, F, M, S, G, Ed. And we have found a solution for getting from me to Ed. Of course, this is one example of DFS doing a faster search than BFS. It's not proof. Okay, so that's a look at depth-first search. The second thing we're going to do in this material is to take yet another look at computing Fibonacci numbers. Okay, onward ho. We've seen 3 different ways of computing the nth Fibonacci number. We started out by just writing a for loop that did this. Then we looked at a mathematically perhaps more natural definition of Fibonacci numbers involving recursion, but we saw that the implementation had exponential performance. And consequently, when we got past around n equal to 30 or 35, performance bogged down so badly as to be unusable. We saw that we could make use of recursion in combination with memoization to get ourselves back to the same performance that we had with iteration. The question is now, can we do even better than that? Can we find a closed form solution, for example? You may remember that very early in the Python Basics course, I had you write a function that computed the sum of the first n integer values starting from 1. And of course, you can use a for loop to do that. You can just compute the sum. But if n is really large, that's going to take a really long time. It's much more efficient to use a closed form formula for getting the sum of the integers 1 through n. In algorithm performance terms, this is order 1 rather than order n. So let's see if we can figure this out. Our recursive mathematical definition of the Fibonacci sequence looks like so. F sub 0 is 0, f sub 1 is 1, and then f sub n plus 1 is the sum of the previous two values, f sub n and f sub n minus 1, for any value n that's greater than or equal to 1. Now, there are many different approaches for figuring out a closed form solution to this. One way that I find easy to understand is to take the nth and n minus 1th Fibonacci values as a vector. Then you can multiply by this simple matrix to get the next vector in a sequence where we have the n plus 1th and the nth Fibonacci numbers in the next vector. It's easy to see that if we start from the vector 1, 0, which is to say f sub 1 and f sub 0, that we can then simply multiply by this matrix to the nth power to get the n plus 1th Fibonacci number. Okay, so we can call that matrix A, and therefore given our vector of f sub 1 and f sub 0, we just multiply by a to the nth power to get f sub n plus 1 and f sub n. And from that, without pretending to amaze you with a bunch of linear algebra, we can just solve for the eigenvalues and eigenvectors of A to reformulate that equation. And ultimately, this does lead us to a simple closed-form solution. That is, f sub n is given by this formula, which I'm not going to read aloud. It turns out that this value, 1 plus the square root of 5 over 2, is what's called the golden ratio. And this appears in mathematics and nature and architecture over and over. Okay, cool. So now we have an order 1 algorithm that is this formula for computing the nth Fibonacci number. Can we do even better than that? Well, isn't that a silly question? How are we going to do better than an order 1 algorithm? Well, remember that performing things like square roots and powers and division is not free, and in finance in particular, we are always eager to get correct solutions as fast as we possibly can. So what can we possibly do that's better than this formula? Well, we could use what's called a lookup table. That is, if we need to compute Fibonacci numbers in some range of values over and over and over again as a routine part of some other algorithm that we're writing, then to save as much time as possible, we don't even want to have to perform this calculation for f sub n. What we're going to do is to just compute all these Fibonacci values in advance from 0 up to, say, 10,000, and just store those in a list in memory. So that computing the nth Fibonacci number is just a matter of looking up the sub n item in this list. In fact, in applications where it's really, really important to save as much time as possible, Lookup tables like this can actually be implemented in hardware and executed even faster than looking up a particular sub-n item from a list. Okay, well, we're not going to be implementing lookup tables in hardware in this course, but that's an idea to keep in your back pocket if you find that you've got to have real high-speed lookups of some pre-computed values. All right, so that's the conclusion for Week 3, Part 2.